You know, medical implants are just these incredible feats of engineering. They're designed to go inside our bodies and literally help us heal. But what happens when one of them, a high-tech steel plate that's supposed to fix a broken bone, ends up breaking itself? Today, we're going to play detective and follow a team of forensic engineers as they peel back the layers of this medical mystery, one tiny microscopic clue at a time. Okay, so this right here is really the heart of the mystery. On the left, you see the x-ray right after surgery. The implant is screwed into the patient's femur, holding the bone together. Everything looks good, it's doing exactly what it's supposed to. But then you look at the image on the right. This is less than 2 years later, and it's a totally different story. That same solid plate is snapped clean in two. And not just the plate, but some of the screws holding it in place are broken too. And that brings us to the big question, right? How on earth does a solid steel plate, something that's meant to be a pillar of strength, fail so completely? It's a real puzzle, one that sits at the intersection of medicine and mechanics. And trust me, the answer is not at all what you'd expect. All right, so like any good investigation, you gotta start with the evidence. And to figure out what happened to the patient, the investigators first had to look at the primary victim, which in this case wasn't the person, but the implant itself. And here it is. This is the actual locking compression plate after it was taken out of the patient. Now, its job was pretty straightforward. Act like an internal scaffold, right? Hold the broken femur in place so it has time to heal. But, well, you can see for yourself, the whole scaffold just gave way. Okay, the timeline here is super important. The surgery happens, then less than 2 years go by, and the patient has an unexpected fall. The x-ray shows the break. Now, at first glance, this seems like an open and shut case, right? The guy falls, the plate breaks. Simple. But for the forensic engineers, this wasn't an answer. For them, this was just the beginning of the real investigation. So, in forensic engineering, the first thing you do is question everything. You have to check your assumptions. Before you figure out what happened to the material, you've got to be 100% sure what the material is. Could it be that this implant was just bad from the start, made of the wrong stuff? So the team took a piece of the implant and did a full chemical workup. And what they found is pretty amazing. When you look at the table, you can see the measured elements on the left and the industry standard for 316L surgical stainless steel on the right. It's a perfect match. I mean, spot on. From the carbon to the nickel, every single element was right where it was supposed to be. Conclusion? This was absolutely the right material. But they didn't stop there. They went deeper, like way deeper, down to the microscopic level. What you're looking at here is the grain structure of the steel. See how those grains kind of look stretched and elongated? That's a telltale sign of a process called cold working. It's done on purpose during manufacturing to make the metal a whole lot stronger. So not only was it the right material, it was made the right way to be tough. So, bottom line? The implant gets a clean bill of health. No defects, no cheap materials, nothing wrong with it. Which means, whatever went wrong, it had to have happened after it was put inside the patient's body. The mystery just got a lot more interesting. Okay, so if the material was fine, the next logical question is, well, how did it break? The investigators turned their full attention to the actual scene of the crime, the fracture surface itself. Because here's the cool thing. When metal fails, it basically leaves behind a story, etched right into the break. And boy, the story this piece of metal had to tell, it was about to blow this case wide open. And get this is the first huge clue. You see those faint, curved lines? They almost look like ripples on a sandy beach. Well, they're actually called beach marks. And those marks are the classic telltale sign that this break didn't happen in one single violent moment. Nope. This means a crack started, and then it grew bit by bit over a really long time. This phenomenon actually has a name. It's called high cycle fatigue. And the easiest way to wrap your head around it is with a simple paperclip. You can't just pull a paperclip apart, right? But if you bend it back and forth over and over again in the same spot, it eventually just snaps. Each one of those bends is a small, tiny stress, but enough of them, and the metal just gives up. And then, when they zoom in with a crazy powerful electron microscope, they find the smoking gun. These super fine lines are called striations. And what's so incredible is that every single one of those little lines marks the crack advancing just a tiny, tiny bit with each cycle of stress. This is the microscopic fingerprint of fatigue failure. There's no doubt about it. So at this point, the evidence is just undeniable. The team knew how the implant broke. fatigue. But that just leads to a bigger question. Why? What kind of repetitive force happening inside the body could possibly be strong enough to break solid steel? To figure that out, they had to rebuild the whole scene, but this time in a computer. They used this really cool technique called finite element analysis, or FEA for short. You can think of it like building a digital twin or a crash test dummy of the whole setup. They modeled the bone, the plate, the screws, everything. And then they could apply the forces of daily life to see where the stress builds up. It's like creating a weather map, but for physical stress. And boom, here are the results. Just like a weather map, blue is low stress, everything's calm. But orange and red, those are the hot spots. That's where force gets concentrated. And just look at this. The highest stress, that bright red spot, is right next to a screw hole. And it is in the exact same place where the real-life implant actually broke. I mean, it's a perfect match to what happened in the real world. But the simulation did more than just show where the stress was. It showed what was causing it. And the culprit wasn't some big accident or extreme sport. The force that was creating these high-stress hotspots over and over and over again was just the simple, everyday act of walking. So how many cycles are we talking about here? How many bends of the paperclip does it take? Well, the researchers did the math, and they estimate the patient took, get this, about 1.6 million steps in those 2 years. Every single one of those steps was one tiny bend. One step is nothing, but 1.5 million of them, that's enough to start a crack in solid surgical steel. So now with all the pieces on the board, the material science, the clues on the break itself, the computer model, the investigators could finally put the whole story together and deliver the final verdict. So here's how it all went down. It began with millions of steps, each one putting a tiny, relentless bit of stress on the plate. Eventually, that stress started a microscopic crack, right in that hot spot the computer model predicted. And from there, with every single step the patient took, that crack grew a little bit more, creeping silently across the steel plate. That final fall, that wasn't the cause. It was just the last straw. It was a sudden shock to a plate that was already about 85% broken. And the official conclusion from the case study? It really says it all. The fall doesn't explain the failure. A healthy implant would have handled that force, no problem. The real cause was the slow, invisible damage building up over time from high cycle fatigue. The fall just revealed a problem that had been growing for months, maybe even years. So, okay, case closed on this one broken implant. But it leaves us with a much, much bigger question, doesn't it? Our bodies are an incredibly demanding environment. Life isn't a short sprint, it's a marathon. It really makes you wonder, how do we design the next generation of implants to truly go the distance, to win that marathon of daily life?